Alright, hello ladies and gentlemen. Tonight we're going to take a look at the geometry domain for the Math 8 EOG. And the geometry domain covers several different areas. So we are going to take a look at these areas of the geometry domain. We're going to look at volume, the Pythagorean theorem, transformations, parallel lines and transversals, the angle sum theorem, and the exterior angle theorem. And we'll go through each of those one at a time. So let's go ahead and get started. We're going to get started with volume. So the first question I get asked about volume is, do I have to memorize the formulas? And the answer to that question is, unfortunately, yes. But the formulas that they want you to know for sure are a cylinder, cone, and a sphere. And what's neat about these three formulas is they are all very similar. So if we look at the formula for the volume of a cylinder, it's the area of the base, which is pi r squared, which is the area of a circle, times the height. That's all it is. And that's true for pretty much every basic geometric solid. It's the area of the base times the height. So the formula for a cylinder is pi r squared h. The formula for a cone is the same thing. It's still pi r squared h, but we multiply it times 1/3, because if we have a cone that has the same radius and height as a cylinder, 3 cones will fit in one cylinder. So we just find the area of the base and we divide it by 1/3. And then the same thing holds true for a sphere, except for in a sphere the radius and the height are the same thing. So we're just taking out this h and we're replacing it with another radius. And so it's pi r squared times the height, which is r, so it's pi r cubed, and then it's 4/3 of that. So 4 of these will fit in here, which means that this is 4/3 of that. So it's a whole entire cylinder plus a cone of the same radius and the same height will fit inside here. So let's go ahead and get started with the cylinder. So for the cylinder, I'm going to make this cylinder have a height of, we'll call this 8 centimeters, and a radius of 6 centimeters. And then just to find the volume, we're just plugging it in. It's pi times the radius squared. The radius squared is 6 times the height, which is 8. And we multiply that all out. We get 904.32 cubic centimeters. That's it. But you do have to memorize this formula right here. And again, it's the area of the base times the height. So if we're going to find the volume of a cone, it's the same thing. We're going to assume that this cone has the same height as that cylinder, and the radius is also 6 centimeters. So it is 1/3 times the volume of the cylinder. In this case, it's 1/3 times 3.14 times the radius squared, which in our case is 6, times the height, which is 8. And we already know that this section right here is equal to 904.32, and then 1/3 of that is 301.44, and volume is always in cubic centimeters. And then last but not least, we have a sphere, and so we're going to have this sphere has the same radius as the cone and the cylinder above, and that should be volume equals. So the volume of this is 4/3 times pi times the radius, in this case, cubed. And so it is 4/3 times 678.24, and we get 904.32 cubic centimeters. Now what I would like you to think about, and I'll talk about this in class tomorrow, and this is just an extension of what we did, if we have a cylinder with a radius of 6 and a height of 8, and a sphere with the same radius, how come we get the volume that's the same? That's my question right there, and we'll talk about that a little bit in class tomorrow. Or if you can think about it, you can tell me what you think about it in class tomorrow. Okay, moving on to the Pythagorean theorem. We've done this before. The Pythagorean theorem says that if we square the legs of a right triangle and add those two together, we get the square of the hypotenuse. Keep in mind that the hypotenuse is always the longest side. So when you're asked to do something like this right here, determine whether a triangle with the given side lengths is a right triangle, we have to assume that this is C because it's the longest. So how do we prove that this is a right triangle? Well, what it's asking you is 7 squared plus 24 squared. Is that equal to 25 squared? And if the answer is yes, it's a right triangle. And if the answer is no, it's not a right triangle. So does 49 plus 576 equals 625? And the answer to that is yes. 625 equals 625. So this forms a right triangle. Now let's take a look at an example where one does not form a right triangle. Let's say we have 5, 7, and 6. So this is going to be our hypotenuse because it's the longest side. This one's A and this one's B. So does 5 squared plus 6 squared equals 7 squared? So does 25 plus 36 equal 49? And the answer to that is no, so it's not a right triangle. Moving on to our next is transformations. So you did these in 5th grade and you did them in 6th grade, and I'm not sure whether or not you did them in last year in 7 plus, but that's what we're going to take a look at today. So we are going to take a look at a figure that I'm going to draw in quadrant 1, and the figure I'm going to draw in quadrant 1 is just a one-dimensional figure, well, two-dimensional figure that looks like this. So a translation just means that this is a slide. So you're just the figure does not change shape. It does not change. It doesn't change shape. It doesn't change size. It just slides. So if we translate this figure down, let's say 4 units, that means we're just going to take that entire figure and we're just going to slide it down. So every point gets translated down 4 units. Actually, let's do 5. It might make our lives a little easier. So if I translate this figure, I'm just sliding it, in this case, down 5. And so that just means that the shape does not change, the size does not change, the direction does not change, just the position on the coordinate plane changes. So translation is just a slide. Up, down, left, right, we could be on the diagonal, doesn't matter. The next one we're going to talk about is a reflection. And if you remember, a reflection is a flip. So we're just going to flip this. In our case, we're going to flip this one over the y-axis. And a flip does change the direction, does change the position, but does not change the side. So if we flip this, we are going to get the same picture. It just happens to be in a different spot on the coordinate grid. And finally, we have a rotation, and if you remember, a rotation is a turn, and you can have rotations. You can have a 90-degree rotation, which is 1 turn. You can have a 180-degree rotation, which is 2 turns, and you can have a 360-degree rotation, which is 3 turns. And really a 360-degree rotation just means that it's ending up in the same spot that it was in before. So if we're going to rotate this figure, we're going to rotate this figure. We are going to do it 180 degrees. We'll do this one right here. So I've rotated this figure 1 turn, then 3 turns, and if you notice, that it has this changed position, and it's also changed location on the coordinate grid. So rotation is a turn. Dilation is a different story. A dilation either enlarges or reduces the figure, and that's where we have a scale factor. Let me spell that a little nicer for you. So enlarges or reduces the figure by a scale factor, and scale factor means we're going to multiply by a number. So if I were to enlarge this particular transformation, I'm taking a look at the purple one again, by a scale factor of, let's say, 1/2, that means each ordered pair will be multiplied by 1/2. So for example, let's take a look at this coordinate right here. This coordinate right here is for 1, and we'll call that point A. So point A is for 1, then A prime, I'm just multiplying each of them by 1/2, so A prime will be the point 2 and 1/2. So my new point, and I'll enlarge this for just for a second, my new point would be at 2 and then 1/2. So A prime would be there. If I called this one right here point B, and that's at the point 1, 1, B prime would be at 1/2, 1/2, because I'm multiplying that by 1/2, and so our scale factor gives us a smaller picture. Same thing, if I'm going to do 4, 4, my new point would be 2, 2, which would be right there. This point right here is 3, 4, so that would be 1.5, 2, which would be right here. And this point right here is at the point 4, 3, so that would be 2 and 1.5. So my new picture, I scaled that down by a scale factor of 1/2, is right there. Okay, our next topic is parallel lines and transversals. Parallel lines are these two right here. They are line AB, this one right here, and is parallel to line CD. The transversal is this guy right here. It's EF, and what happens is that transversal cuts those two parallel lines into two sets of angles. We have angles 1, 2, 3, and 4, and 5, 6, 7, and 8. And pretty much all you need to know about parallel lines and transversals, if these two angles are opposite one another, like 5 and 8, 7 and 6, 1 and 4, and 3 and 2, if they are opposite one another, the angles are congruent, which means they are exactly the same measurement. Adjacent angles are angles that are next to one another, so like 6, 8, and 5 and 7, 2, 4, 1, 3, or 1 and 2, 3 and 4, 5 and 6, 7 and 8. And if they are adjacent angles, they are complementary. No, they are not. They are supplementary, which means that their sum equals 180 degrees. That's the degree of a straight line. Corresponding angles are angles that are in the same position or in the same, just in a different location. So angle 1 and angle 5 are corresponding, angle 2 and angle 6, angle 3 and angle 7, angle 4 and angle 8. They're just in the same position, but just in a different location. They're in corresponding locations. And corresponding angles are also congruent. So for example, angle 1 and angle 5 are corresponding, angle 2 and angle 6 are corresponding, angle 3 and angle 7 are corresponding, and angle 4 and angle 8. And what you have to remember also is if the little angles are always the same, so 1, 4, 6, 2, 3, 6, and 7 are all the same exact measurement, and then 1, 4, 5, and 8 are all the same exact measurement. Okay, finally we're moving on to two theorems for triangles, and the first theorem is our angle sum theorem. And basically all it's saying is the sum of the interior angles, and interior means inside, the interior angles of any triangle. That sum is equal to 180 degrees. So the measure of angle A plus the measure of angle B plus the measure of angle C has to equal 180 degrees. So if angle A is 95 degrees and angle B is 35 degrees, then angle C has to be 40 degrees, because 95 plus 35 plus 40 has to be 180 degrees, and that works for any triangle, whether it's a right triangle, isosceles, scalene, equilateral, obtuse, acute, doesn't make a difference, has to equal 180 degrees. Our next and final section for geometry is the exterior angle theorem. So if A, B, C, and D are on the inside of the triangle, we also have angles that are formed on the outside of the triangle. So the measure of an exterior angle of a triangle is always equal to the sum of the measures of the two remote interior angles. So, for example, these two right here are the remote interior angles, and this angle right here is the exterior angle. So what it is saying is that the measurement of this angle is equal to the measurement of these two. So if angle 1 is 60 degrees and angle 2 is 70 degrees, so if the measure of angle 1 is 60 and the measure of angle 2 is 70, then the measure of angle 3 has to be 130 degrees. And that will work with any exterior angle. We can have the exterior angle here. We can also have an exterior angle here. We can have an exterior angle here. We can have an exterior angle there. Okay, these are the questions. This is there are 12 questions for, I believe there's 12 questions for geometry. If you have questions about the questions, you can come to Smart Block next week. I think this week the geometry day is on Thursday, but you can also ask these in class tomorrow. So there's questions 1 through 6 and questions 7 through 10 right here. Okay, have a good night.